past 10. Thank you very much. And then we have the first session with the 3 outstanding papers. The first will be by Artur Shevtsov, Roman Ryzantsev, and Maxim Davidov. Thank you for coming. This will be on geolocalization of sequential aerial data using deep learning. And the session itself is focused on robotics and computer vision. So the second paper will be presented by Ivan Husarev. And title is MSGPT, musculoskeletal generative pre-trained transformer for movement pattern analysis. And the third paper will be on object tracking, low FPS self-supervised, low FPS multiple object tracking for UAV. The paper will introduce 5 FPS benchmark and methodological advancements. So I believe that the program is very, very interesting. I'm looking forward to hearing your great presentations, and perhaps you're looking forward to hearing a lot of interesting questions. So we'll have a great discussion here. Though it sounds a little bit more Trumpish, and that's okay. So let us start our first session. So the first presenter will be Artur Shevtsov. The floor is yours. And please go ahead.
Maybe I will add a couple of organizational details. So we have all presentations grouped by a topic into sessions. And we will have a lunch break from noon till 1 p.m. And after each session, we're gonna have a coffee break. So, and also today, in the end of all sessions, we invite everybody to come to, I forgot how we call it, social event. And I think we can discuss it later. Yeah, so I think this is it. Yeah. The best of luck.
Okay, thanks. So good morning, everyone. I'm happy to present you with our ongoing research project on geolocalization of sequential aerial data using deep learning, which I'm honored to do with my supervisors, Roman Ryzantsev and Maxim Davidov. Here's a short plan of what I'm going to cover in this presentation. We'll start with the problem statement, motivation, its main challenges. I'll then proceed to a high-level overview of current research work that is done in attempt to solve this problem. We'll touch on data sets, different research approaches, and the research gap that we found during our analysis. We'll then proceed to our approach that we implementing in our research project. I'll say a couple of words on early results and future work that we are going to do within the scope of our project. I'll then be ready to answer any questions if there be any. So let's start with problem statement, motivation and challenges. Basically, the so-called visual geolocalization problem can be defined as mapping any image to a set of geographic coordinates representing some location on Earth. In our particular case, we would like to focus on images that are taken from cameras of unmanned aerial vehicles, aka drones. Yeah. So why bother with this problem? So first of all, visual geolocalization can significantly improve autonomous drone navigation in conditions where GPS is either unreliable or inaccessible at all. So taking even step further from that, if we have robust and precise visual geolocalization, it means that it's now possible to launch completely autonomous, that is pilotless drone missions. That's and of course, the many different domains can benefit from that, since many processes can with drones involved can be automated. So now that we know what is the problem, what we know about our motivation in solving it, it's worth touching on main challenges that we are facing when solving this problem. So first of all is data collection. Practically, it's really difficult to obtain data from UAV cameras, especially in conditions that I've just mentioned about the scarcity of GPS signal. Also, even if we do have geo-labeled data either from drones or from satellites or whatever, there are number of environmental variables that's basically that can significantly limit the performance and generalization of computer vision models, including seasonal patterns, weather conditions, time of day changes, and changes in urban planning. So now that we have a sort of high-level overview of the problem, let's proceed to a short overview of current research that was done in attempts to solve this problem. So we'll touch here on data sets, main research approaches, and the research gap that we found during our research project. So let's start with data sets. And first, and perhaps the most popular data set for UAV geolocalization is called University 1652, publicly released in 2020. It practically contains 15,000 satellite and UAV images. And what's important here is that UAV images, quote unquote, are represented by synthetic images that were basically scraped from Google Earth API. So they're not real drone images, but rather 3D renderings of some popular places around the world. Another data set that was released in 2023 is called Dense UAV. And this is, to our knowledge, is first publicly released data sets with real UAV geo-labeled data. And it contains around 20,000 UAV view and satellite view images of 14 different university campuses. And another interesting data set that I want to show here is called WISLOC, probably last publicly released data sets on UAV localization. It contains around 6,000 consecutive photos collected during 11 drone flights over different geographical areas. And what's interesting about data sets, the data was collected on higher altitudes that's from previous data sets. So it's in range between 400 and 1,800 meters. Summarizing, we have University 1652, which is the most popular one, as I said. And overall, as we can see that earlier data sets, they tend to be synthetic in terms of UAV photos. And it's only in 2023 that there appeared data set that contains real images captured by drone cameras. And what's also important is that earlier data sets, they're not sequential. And by sequential, I mean that by not being sequential, I mean that these earlier data sets, they contain discrete photos of different buildings in different places on Earth. But But in real setting, we mostly, we basically have drone missions that are capturing cameras are capturing consecutive frames of photos, and they basically have relations between images. So that's not what we see in these earlier data sets. Yeah, so that's data sets. Now let's jump to current research approaches. I'll touch on two examples of research papers that we found particularly interesting. So first research work was called as Orientation Guided Contrastive Learning for UAV View Geolocalization. Basically, this work is now currently state-of-the-art on multiple UAV localization benchmarks. And essentially, it uses satellite and drone view pairs of images to estimate the different view alignment. So the idea is to train a model that is able to accept input drone image, unlabeled image, and find the closest match of satellite geo-labeled image, and that's how the location of the image is estimated. Another work that I want to mention here is called Pigeon, Predicting Image Geolocalization. This is a not specifically UAV, but rather general image geolocalization work that actually impacted our project in terms of its development of multi-level prediction pipeline. So in essence, the develop approach allows to localize different images on the entire planet, but still maintain a relatively good granularity of our predictions. And I'll touch on the component we implemented in our project later. So now that we considered data sets and research approaches, let's touch a bit on the research gap that we found during our research. So 2 points I want to mention here. First is that as to our knowledge, none of the analyzed research considered utilizing the so-called sequential nature, which is inherently present in drone captured photos. The point that I already somewhat mentioned, where we have the relationships between different consecutive photos. So in other words, most approaches they consider that they treat they treat images as single and completely isolated images from different images, and do not consider images sequentially. And another point that I also already somewhat mentioned is that most of the research work currently on UAV geolocalization was validated on University 1652 datasets, which, as I mentioned, is synthetic. So the photos, as a reminder, they were collected from Google Earth API, and these are basically synthetic renderings. And they are not, again, they're not sequential, but they are discrete. While in real-world scenarios, we have drones flying over some territories, constantly collecting the data, and this is far from most realistic scenario. So that's why we are developing our research project. We want to close these two gaps and validate our approaches with. So firstly, we would like to develop a sequential model approach, which considers a relationship between different frames. And secondly, we would like to validate our results on more real world, so to speak, data sets. That I will touch on a bit later. So let's now discuss our approach we are implementing within the scope of our project. So here I will talk about data set collection. I'll talk about tests and training data sets, and I'll cover two different aspects that we would like to implement in our work from technical perspective, which are multitask learning and sequential modeling. And finally, I'll touch briefly on loss function and our evaluation framework of projects. So let's start with the data. As a evaluation set, we use Wizlog that I've just mentioned in the previous section. Again, as a reminder, it contains around 6,000 consecutive photos that were collected on 11 different drone flights. So we take the 95% of these data sets as a test set, and remaining 5% we transfer to our training data. And for the locations that are present and in these Wizlog data sets, for the very same locations, we have collected data from 2 different satellite providers. Specifically for training, and we also collected synthetic data for training using AirSim flight simulator. So here we have we also were able to obtain images in different weather and seasonal conditions. So that's why it's multiplied by a factor of 3 here. So the total training data sets is almost 32,000 images. Now let's touch a bit on our technical aspects of our work. And the first one is multitask learning. So again, our goal here is to develop a model which is capable to produce relatively fine-grained prediction over a certain region of interest. This region can span quite large geographical areas, and in other words, we would like to develop a model that is a kind of expert over some geographical area of interest. So the challenge is here is to maintain a high level precision while covering vast geographic areas, because when we are dealing with geographic coordinates, latitude and longitude, even a very, very slight deviation from these coordinates can lead to very significant errors that we have to face. So the challenge is here really that from the one side, we have to cover large geographic areas, and from the other side, we still want to achieve relatively good precision over this average. And that's why we developed this multi-stage learning approach. So the idea here is to divide the initial region of interest by smaller subsets we call geocells. And on the first stage of our prediction pipeline, we basically would like, given an image, we would like to determine to which geocell does this image belong. So we'd like, in other words, we'd like to classify this image to assign it to some particular geocell. And now that we have this geocell, we know the geographic center of this geocell. We basically would like to predict the deviation from the center of this geocell to estimate fine-grained and precise prediction in geographic coordinates. So as an output, we get 2 deltas on latitude and longitude that basically represent how far and in which direction we need to go from the center to obtain a final prediction. So yeah, that's the multitask learning component. Also, there is a sequential modeling feature that I've already mentioned a couple of times. So in detail, here's the architecture that we plan to implement within the scope of our project. So basically, the core components is that we would like to process images sequentially. We would like to take a sequence of certain size as an input, and as an output, we would like to we'd like to predict a sequence of geographic coordinates that are assigned to this image. And the idea here is to leverage the information that we get not just on a single image, but on the entire sequence of the image, and compare it with an attention architecture component, and to basically estimate how much information do we have in each image that would help us classify and get regression predictions of final coordinates. So now let's touch on loss functions and evaluation metrics that we use within our project. So for classification metrics, we use scale divergence, cross entropy, and sphere phase angular loss. The idea is basically to put images belonging to different classes close to one another. That is to minimize interclass difference while maximizing intra-class difference between different, sorry, not difference, but deviation between different classes. And for regression loss, we simply use mean squared error over geographic coordinate space. As for evaluation, our primary classification metric is, of course, accuracy, and we also have supplementary metrics such as precision, recall, and F1 score per each class. The main regression, and indeed the main target metric, is the so-called Haversine distance, which is basically the distance between two geographical points if we project them on a sphere. So we basically treat the Earth here as a sphere, so to speak, and determine the distance in meters or kilometers between 2 points with this Haversine distance function. Now let's touch on some early results that we were able to obtain within our project. And as a reminder, here's the part that we have implemented from our as of now. So we still process images discretely. We only take one image as an input and get one. Sorry, it's not. There is a mistake here. Should be not a sequence, but just one pair of coordinates as an output per input image. So these are the results we were able to obtain. Basically, the accuracy on the Wislog test sets that I've just mentioned here, we were able to keep it as 72%. As for Haversine distance error for items that we have correctly classified, we managed to get 2.23 kilometers errors, and there are also misclassified items, and that's a bit tricky. So the point here is that Wislog dataset contains 11 different geographic territories, and these territories are located very far apart. So that means that if our model classifies some image incorrectly, that means that the error can basically jump into hundreds and even thousands of kilometers. So that's why for misclassified items, we have basically huge error, and this huge error skews the average distribution of our general errors. And finally, the future work that we plan to implement here is just to develop this second part of our implementation, which is sequential processing. So this is basically the part that we plan to finish within the scope of our project. And I believe that's it. Thank you for your attention, and I'll be happy to answer any questions.
Thank you very much. Are there any questions in the? Yeah, go ahead. Just to make important things recorded.
I wanted to ask, what is your motivation for this project? What is like practical implementation of the work you do?
Yeah, thanks for the question. I think we can return to this slide. So yeah, basically there is an ongoing, very serious problem in any area that uses unmanned aerial vehicles, is that the GPS signal is often unreliable. Okay, so that means that when we use drones for any purpose and the signal is unreliable, it means that we are unable to navigate efficiently, and this can lead to loss of drones, for example, or some other disruptions in operation processes. So in so-called GPS denied conditions, the GPS independent geolocalization would be really beneficial. So that's the main motivation. And this, as you see, can be used in any domains that uses drones for its operations.
1, 2, 3. Oh, okay. Okay. I have a question about like the model and dataset generally. If I remember correctly, you mentioned 11 different regions and 6.3 thousand images.
Yeah.
So I assume it's like really limited to like the amount of data it contains, and the model is only capable to like predict one of the regions it knows about. So my question is, how much data is needed to like cover some bigger region, like the whole city of Lviv or maybe Ukraine, and whether it's possible and even required for anything?
Yeah, we're still kind of figuring it out. And as far like even for these 11 different regions that we work with currently, we observed like the distribution of number of images is highly skewed. So for some regions we have like 1,000 images, and for others we have as few as 30 images that we have to deal with. And as we observed, it doesn't really impact the model to perform well on. So if we have, for example, many very few images for some regions, it just means that we will not be able to go out from this region and classify generalized to unseen regions. Okay, so it doesn't really matter. So for some regions, we just have to cover it with consecutive photos, and we just have we can have overlaps between different images, but we cannot have anything missed, because practically the model is basically searching for some geographical cues that it can use for for localizing it. For example, if we see some very special type of building that you cannot see anywhere in the world, you can basically the model can right from the scratch understand that that's around where it is. So I seen this building somewhere and I see it now. So that's how it works. Or we can use some landscapes cues such as water, different patterns of streets, and yeah, and so on. So it doesn't really it's so as long as we cover some region, we can handle it as at least as per our current results and what we observe.
Thank you. More question?
Yes, I have a question. First of all, thank you for the presentation. You partly covered the question during the presentation, but maybe you can share more details. The question is how the error is propagating throughout the network, especially considering this multi-learning task approach. Thank you.
Yeah, that's a very good question, since we struggled a lot with this multitask setting. one of the problem was that our model was able to, for example, do very well on one task, but performance was inadequate for another task. So we have a good performance on classification, but regression model was really struggling. So yeah, that's I don't have like very easy answer to these questions. It requires a lot of experimentations with different losses, with different coefficients that you apply for these losses. So it's in our experience, it really required some experimentation and trial and error, and yeah, that's how we kind of optimize it.
Thank you. Questions? Okay.
Thank you, Artur, for the presentation. Also have a couple of questions. So maybe a follow-up question on the loss. I'm curious, you mentioned that you have a set of, say, disjoint regions, right? That can be far away one from another. And so I'm curious, how do you compute a loss? Because it seems to me that, for example, if the model guesses wrong, and that region is actually very visually similar to to ground truth, but geographically it's very far away, would this difference in distance, how would this difference in distance impact the loss?
Yeah, so basically, in terms of distance loss, as I said, we only use mean squared error loss, and practically that means so if the error is very distant, this means that the loss will be obviously higher. But it also is heavily impacted by classification, since we have 11 different classes, but some classes are closer to one another than other classes, and that means that some like closer classes errors that are located geographically closer, they're not punished that much by the model is not punished that much by these types of error. But yeah, that's still also a problem we're currently working on, and I guess at least partly the sequential modeling approach can mitigate it, because even if we like on a single image level, if we have some visually close objects that look similar, the model can confuse them. But if we have a sequence, for example, from 10 images, we can hopefully arrive and capture some different geographical cues that distinct this particular geographical area that we can so that we can correct for the initial problem with visually similar geographical regions. Yeah, I hope that answers the question.
Thank you. And the next question is, do I understand correctly that this knowledge about visual features like during the training should, as I understand, should be somehow encoded into model weights or something like that?
Yep.
Because you do not compare it to, for example, some of the database of examples or something like that.
Yeah.
So my question is, for example, if we are speaking about like updating the region because it changed or something like that. So what are the ways to update? Only retraining or something else?
Yeah, I think yes. So first of all, you were correct. That's basically the knowledge of geographical location is basically encoded in model weights. So yes, that's correct. And probably your second question is also, I would also answer yes, since that's a good question, and we didn't really discussed it within our project, but as to my best guess and knowledge, I think that if the region changes significantly, we have to retrain our model, or at least update our data sets with, for example, with new satellite images. Yeah, and something like that, or probably fine-tuning the model would be also suitable if some areas change significantly. There is a question still.
I have 3 questions. First of all, I'd like to know, do you align your input images by compass before passing to a model, or just passing this arbitrary rotation?
What do you mean by aligning by compass?
Rotation so that top is north, bottom is south.
Yeah, this problem is I think it's solved on the stage of data collections. So we're working mainly with satellite images. So when we collect them, they all have the same orientation. So we basically don't have to do anything with those images before inputting them to the model.
And what about photos taken by drones?
And I think I think they're not aligned with satellite images, but that's not the problem, I guess, since the center is preserved. And what we want to do here is basically to predict the center, not the orientation. We just want to. Anyway, we also have some image augmentation where we included rotations. So practically no. So drone and satellite images are not aligned, but I guess that's not the problem in this context.
But I think in your training data, there are a lot of photos aligned by north-south, and some photos not aligned.
Yeah, but they would be anyway. We use rotation as an augmentation pipeline, so that's not really.
Okay. So you have rotational augmentation.
Yeah.
Arbitrary.
Yeah.
Okay, good. So the next question is your method really limited to photos taken by drone vertically, just to the ground, or it can work with any photo, for example, taken by car, by ground vehicle, and so
on? We haven't tested it, but I think the performance would not be adequate, certainly on ground images, as of my best guess, since these are very different types of data from satellites, from drones, from high altitudes, and ground images are very, very different from these photos. So they contain different information. So I doubt if we would have any adequate results on those images.
Yeah. Okay, thank you. And the third question is, in your method, you have encoding of your input images into a vector of, I know, maybe 128 weights, yeah. Yes. So it's some small vector, feature vector. And I was thinking about using this feature vector, the query to some vector database with a lot of images and obtaining coordinates in such way.
Yeah, that's what we've seen in most other research approaches on UAV geolocalization. And I think we can eventually try it and compare these approaches with ours when we do some benchmarking in future. And yeah, but that's definitely one thing we can do. And so compare this methods when we have this information encoded in model weights with that database approach. That's totally valid, I think.
Okay, thank you.
Thanks.
Thank you very much. Not yet. More questions here from the audience? From the virtual participants, just please raise your hands if you have questions over there. So while you're thinking, I still have questions, and please go ahead with your presentation. As I said, not yet.
Sorry. Just let me join again.
Sorry for asking you to pop it up again. I just want to see the slides with
yeah, sure. That's not a problem at all.
with your data sets and measured results.
Yeah, just 1 second.
It's number 33 as far as I remember.
So
yeah,
this
oh,
one?
no, this one.
Yeah.
This one is no.
Okay,
there was a slide with some measurements. With some measurements.
Oh, okay. Evaluations.
Evaluations, yeah.
Yeah. So here you go.
This one. I have a couple of questions here. The first is, can you please elaborate on how good or bad the result is compared to the state of the art?
It's really, it's not that easy to elaborate on that since, as I mentioned, this Vizlog dataset, it was released in 2024. So as to our knowledge, we haven't encountered yet any papers that were benchmarked on these datasets. And the previous UAV geolocalization benchmarks, they're not measured in kilometers, but rather in, because those are based on image retrieval approaches. So basically, these are kind of approaches that we evaluate on the percentage of correctly retrieved nearest neighbors, so to speak. And we have not metrics in kilometers as we do here, but metrics in percentages. So the percentage we can, of course, evaluate, but that's a different kind of problem, I think. So I don't really know and some easy way to compare it. Yeah.
Yeah, what does your backbone say? Is 71.9 good or not? And why?
I think that's decent for as a start. And because with that, as you see, for correctly classified images, we on average have 2.23 kilometers, and correctly classified, they compose 72% of the images. So that's basically means for 72% of the images, we are ready to, on average, give as good predictions as 2.23 kilometers. And that's probably still not an approach that we can implement to real world scenarios, of course, but as of my guess, I think that's a decent start.
Okay, my second question is about the outliers. 257 on validation and 347 on the test differs quite substantially from correct results.
Yeah.
So what might be a reason for that?
Yeah, the reason here lies in the nature of the data set. So basically, different classes here are represented by different drone missions over different geographical areas. And the thing is that these geographical areas, some at least geographical areas, are located very far apart. So in our particular case, this data set was collected in mainland China. So, and some territories were in the north of China, some territories were in the south of China, and the distance between these two territories is something like 2,000 kilometers. So that means that if we misclassify a sample which is very far apart from that from the true sample from the true class, sorry, that means that the error would skyrocket.
So this single case kills all the batch.
Yeah.
Okay, and perhaps my final question is about drone missions. As far as I understand from my intuition, drone missions are, well, predominantly over the rural areas where the images and the patterns are quite repetitive.
Yeah.
So what is your estimation of correct and incorrect classification in these conditions?
It's hard to evaluate straight away, but yeah, my guess is that the performance would also degrade here. I wouldn't be able to say by how much, but yeah, that's a completely valid challenge that you mentioned, that we have to classify and predict the coordinates over very similarly patterned landscapes. And yeah, that's indeed another significant challenge of
Would
geolocation.
your sequential approach help reduce the error?
Sorry, could you repeat?
Would your sequential approach
Yeah.
help reduce this error in repetitive rural conditions?
I think yes, because when we're dealing with longer sequences, it is more likely that we have extract some cues, even if we don't have many, but hopefully we will be able to arrive at some geographical cues that would enable us to classify it correctly.
So you mean that longer sequences, less repetitions?
Yeah.
Okay. Okay. Thank you very much. More questions?
Thanks.
Let us. Thank you. So, next speaker is. Our next speaker is Ivan Husarov. Ivan, floor is yours. Let's go ahead.
Okay. Good morning, everyone. Today I'm going to present my proposal paper. So it's a presentation of it. A musculoskeletal generative pre-trained transformer for movement pattern analysis. The main idea is to predict movement patterns from textile descriptions. Let's imagine, like, you say, walk 2 steps forward, then slightly turn left, and then like move 2 steps forward again. And it should be represented somehow in muscle activations. I'm doing this work with my supervisor. It's Sergey Yakovenko, associate professor from West Virginia University. And yeah, let's go straight to the motivation part. Yeah, talking about motivation part, we have these main challenges. We can represent movements in terms of muscle activations or in terms of joint movements or joint torques. But representing in muscle activations gives us much more variability. We can estimate joint torques from these muscle activations and vice versa. So the main idea of this project is to create easy way to generate synthetic datasets of these muscle activations. Here we are focusing on lower limb gaits, lower limb activations. So it's all about walks and turns. We are focusing on slow, regular, and fast walks, and on left, right, slide turns. Okay. Yeah. Here you can see our research goal. On the left side, we have kinematic data. Kinematic data is data we are actually capturing from motion. Yeah, we have this small EMG capturing mechanisms attached to limbs. Like here, every dot is this mechanism that captures actuation or its position in space. And then we could generate like some freaky skeleton moving with this stuff. Yeah. And or we could just use these muscle activations as a data as an input for we could use nothing but only natural language instruction like walk forwards and etc. Yeah, and we could generate the same or almost the same. Yeah, it would largely reduce this need of kinematic data and kinetic data. That's actually one of the struggles I faced when I worked while I was still working on this project. Yeah, that's the main struggle, I would say. Yeah, from here, it's all about muscle control, computed muscle control. It's how muscle activations are computed from kinematic data. Right now, it's an optimization technique. It's not performed with deep learning. It's more like classic machine learning. Yeah, and here is like the most recent works in this field. This is synthetic data sets of multiple activities. It's somehow labeled, like it's for run, for jog, kick, jump, etc. But we only focus on walks. And also, these data sets is not, yeah, it's not doing what we want. It just gives us the synthetic data. So what is yeah, research gap. Research gap is a high computational cost of CMC. Of course, we need this kinematic data for some simulations, for maybe training some agent-based models, which need these simulations. So we need this kinematic data. It's hard to acquire. It's slow. We need people, etc. Yeah. It's limited because it depends on limb size. Like we need different captures for children, for like elderly people, and yeah, it depends. Yeah, and what is the main research gap here is we need to address this sub-gate temporal dependency. For understanding gates is 2 steps. Like when you have 1 step, 2 step, and 3rd step, it was a gate. Yeah. And here is this visualization of it. So we need to address somehow these steps and connections between them. If we need some complex instructions, like multiple different types of movements, we need to address this dependency. And here is a research question: can transform model predict these muscle activations? How it would predict? Should we predict like data point after data point, or should we have intra-gate predictions, multiple gates? We don't know which would be better to predict and which would capture the largest chunk of movement. Yep. Here we define some constraints. We defined, let it be 8 muscles, 4 muscles for each leg, 2 flexors, 2 extensors. Flexors are muscles which I don't know how to describe flexors, which activate when you like make this motion, and extensors when you like doing the reverse motion. They are working in interface, so their equilibrium had to be we have to deal with it, yeah, and have to somehow maintain it, and we have to maintain physiological plausibility here. Yeah, and we also scaled our data points to only 30 data points per 1 gate. Okay, here's actual transformer model. transformer architecture. It consists of 8 parallel output layers and 1 gate prediction head. This model is autoregressive. So gate head, when it predicts end label, it should stop predictions. Yeah, making predictions, and the sequence would be done. Why 8 parallel muscle activation heads? Because we have 8 muscle working in parallel, so we need to somehow keep this alignment between them. Here is we are making here 1 pre-training. Okay, not like that. Our model development cycle consists of pre-training and fine-tuning. So for pre-training, we are taking a larger amount of moments. We also acquire backward movements, maybe some kicks, jumps, jogs, etc. And also we have some synthetic data for turns. Here you can see 1 gate for a turn. It's described with vastus lateralis muscle. It's extensor. It's like below the hip. And here is slight turn, synthetic turn to the left. As you see, this extensor for left leg is working less for right hand, for right leg. Yep. Okay. Here's pre-training strategy. It's also we use this BERT encoder and for natural language instructions, and try to like predict the gate from first gate from this instruction. Okay, and then we use fine-tuning on labeled instruction to muscle activation sequence. Okay, here is some simple diagram. It's just easy. We are now on pre-train step, on developing pre-train step of the model, and as I see now, we should be iterating after we do it. Yep. And here I wanted to show like 2 different gates from the dataset. It's also like 2 flexors, 2 extensors, as we wanted to acquire and wanted to predict. It's for 1 for slow speed, 1 for like regular speed. And here, even here, you can see like differences in muscle activations. That's what we want to predict. It's already scaled, and no, it's not already scaled. Okay. Yep. Yeah. So I know Sergey likes how project is going. I like how project is going, and we are looking forward to like somehow to know how to combine this intergate predictions and see how it would stick together. Yeah. Thank you.
Thank you very much. I believe we have a lot of questions. Who is the first? It looks like a good tradition already. I start the conversation. Okay.
I like question about motivation. I know about this work a little bit more as we in one group on master seminar, and I know that this model would be useful for prosthetic limbs, as I understand, and I'm interested like what is like the whole I would say pipeline like of implementation this technology, like this model into actual prosthetic limb solution, and how it will improve current solution, for example, mechanical, like how it differs, how it's better, maybe, you know, from mechanical prosthetic limbs that are actively used right now, actually.
Okay. Thank you for question. I want to say that like for this solution, we are actually generating a lot of synthetic data for developers of these prosthetic limbs to test it on, at least in some synthetic environment. I don't know. Yeah, so we plan that this solution would work for like multiple developers in which work with this neuroscience lab where Sergey is working. So it would not be integrated right into prosthetic limb, but it would be used for training, maybe for like prosthetic testing, and maybe somehow adjusting muscle activation data of stroked patients. Yeah, like not adjusting, but trying to find this equilibrium, I would say.
Okay. Thank you. More questions? Yep.
My question is, are you going or maybe already using some simulation to verify how good is your prediction?
Okay, thank you. If I get it right, you ask like, can you use some simulation? Yeah.
Yes.
Okay. Yeah, you can use a simulation. You can use OpenSim simulation. It's simulation engine which can compute forward dynamics and forward dynamics pipeline, which would result in joint torques, which can be shown on this freaky skeleton walking.
And are you using this now to understand is your prediction good or not?
I'm using it like from the other side. I'm using inverse dynamics pipeline to generate these muscle activations. And I'm right now I'm not validating it with this simulation solution, but I validated with some statistical flows.
But how you know if, for example, in statistical you have 3% of deviation, but your model will just fall on the ground?
We are trying to keep these physical constraints straight, like flexor and extensors equilibrium. So flexors, muscles that are working when you do that, and extensors, muscles that are working when you do that, are working in different phases. Because if they work in same phase, the model would fall. Yeah, maybe the walk would not be as human as it is. Yeah, but the model would be keeping like not falling down. But we plan to validate it, of course, with this simulation solution.
Yeah, okay, thank
by
you.
The end.
I'm looking for validation.
Okay.
I love the second question. It resembled me the cross evaluation with the robots of General Dynamics. Do you plan this? Their models do not fall.
It's hard to answer.
Okay, too early perhaps. More questions? Okay, while you're thinking, I still...
Yeah, so could you please go back to the architecture of your model?
Yep.
So I would really appreciate if you could briefly cover, for example, what is an input, what is an output, and how during this model pass input transforms to output.
Okay. We have text inputs, which is our instruction. And
for example,
like walk 2 steps. Okay, walk 2 steps, simple instruction. Then walk 2 steps, we with this BERT encoder, we transform it into latent space. And okay, I see there's some parts are missing here, yeah. And then we through pre-trained layers decoded into its 8 30 by 9 activation layers. Yep, and one gate head, which then has its different losses combined, and training cycle like begins again.
So it would be also interesting to see what is the loss, and maybe some training curves. For example, here is my training loss. Here is my validation loss. Just to be able to see what's happening there.
Yeah, I would say we just couldn't do it like until now. We are only on pre-training stage, and plan to finish it till. Yeah.
Okay, and maybe you could briefly also explain what is pre-training and fine-tuning in this case, and why do you need that?
We need that to have a bigger range of muscle synergies somehow explained in this latent space, not latent space but hidden layers of neural network. So we use pre-train for multiple different activities, not only walks, but also jumps and kicks. And fine-tuning, we have this small grain data sets we constructed with instructions. Yeah, and then we use these frozen layers. We pre-trained to create final model.
Thank you. I'm also curious, for example, this gate cycle that should be the output of the model. How is it differs based on I don't know, the size of the human or something like that? Is it the same for all humans, or body shapes, body weights, height, and so on? So how do you account for this?
Okay, about this question, thank you. I wanted to address it just right here. It's about, yeah, this dataset part, synthetic part. In this dataset, synthetic muscles in time, we have like these gait cycles scaled. Not even gait cycles. We have these limbs of humans and motions scaled to some sample human being. Yeah, that's why we are focusing like almost fully on these data sets and not some other data sets because they are not scaled properly.
Okay, I see. Thank you.
Thank you. Any more? Oh.
That's one question. What do you see about your model capability? How well would it generalize to some more complex text input, or is it just for very simple commands?
We plan to make it only for few very simple commands because also even we having this data set, it's not enough to train like fully capable model. We are planning only to focus on different speeds of walks and slide turns, and only for like at most 3 instructions. Yeah.
So it won't recognize like jump 3 times, then one more time go, then jump.
Yeah, something like that. It won't recognize. Yeah.
Okay, thank you.
Thank you for stealing my first question. Do you guys have more attempts to steal my second question? No way? Okay. My first question was a little bit more general. Just imagine that you were successful in this project and you have a brilliant prototype which does whatever you instruct it to do in text. I'm sleeping in my bed. I'm just trying to wake up. Instead of waking up, standing up and going to do my coffee myself, I instruct your prototype, please go to the kitchen and make a coffee for me. Bring it back. Would it work? Would it be possible? I mean, in as a concept to generalize up to these complex instruction? And what would you need to do extra to what you plan to do here?
Okay, yeah, it's a great question. I would say like going to the kitchen is next level of complexity of instructions. It's not just some locomotion instruction like walk, kick, jump, run. I don't know, maybe if you have data sets of walk in your home.
There are some data sets for impaired elderly people and their home environments. There are the data sets on that.
I think it's possible, but it's hard to imagine how to combine, like maybe using this model several times.
I mean,
or
coffee,
having
how
some...
to combine coffee and locomotion?
Very
Very well combined. You can't locomote without coffee in the morning.
Yeah.
Okay, could you please go forward to your conclusion slide? You know, I looked at the slide and it looked to me over-optimistic. Could you please prove at least the first statement?
I like it.
This is biased. What you're saying is biased.
Actually, yes.
Could you please find an unbiased argument for me?
Unbiased arguments. I see as a good point that we actually created this synthetic pipeline for generating synthetic data sets for that. That's actually the thing is not present in other research.
Yeah. What is your estimated performance based on the use of the synthetic data set? Would it improve the state of the art?
No, it would not break the state of the art, of course.
So what's the utility of generating a synthetic data set?
It's easy.
What was the motivation? Thank you for the word. For generating this synthetic data set.
We can generate a huge amount of locomotions in, I don't know, very easily.
So what? If it doesn't help you?
It helps.
Okay.
Oh, not the state of the art level, but it helps.
Okay. More questions?
Thank you for your presentation. First of all, and my question is, can we expand this synthetic data? From the previous question was, can you instruct your model to do you a cup of coffee? Can we expand the synthetic data that will create a cup of coffee for you? Like you said that you created a synthetic data that helped your model generalize it.
Okay, thank you. I see what you mean, but I think it's not about one data set. I think answering this previous question, it would be like some sort of agent-based model, which would use this model and maybe some upper limb not locomotion, but movement model for different tasks. I don't think that having a lot of instructions of different limbs, of different movements is a good idea here.
Well, if you enable your system to reason very well based on the set of these instructions, why not? It's more about reasoning, not about collecting data. More questions? So thank you very much.
Thank you.
And I'm about telling you who is our next speaker. Oops. So our next speaker is Mikita Varenik. Please go ahead, the floor is yours. And the title of the paper is Self-Supervised Low FPS Multiple Object Tracking for UAV, and so on, so on, so on.
Yeah, so hello everyone. They would like to present my paper proposal for for improving self-supervised multiple object tracking in environment of low frame rate per second. And I would like to give acknowledgements to my professor advisor, Igor Krashiny, professor of Ukrainian Catholic University. So overall, to give you a short introduction, multiple object tracking is a task of continuously detecting and then re-identifying different entities across a video stream. So there are multiple real-world use cases, like for instance, surveillance, monitoring, self-driving cars, UAV, traffic analysis. So here's an example such model. So as for UAV specific challenges, this complex task is further complicated by frequent angle changes, continuous rapid shifts in lighting and view angles. Also, in cases when we need to have operational awareness and centralized real-time tracking, we cannot afford to process all the data in good quality, so we need to reduce it to low FPS. Another case is that requires low FPS is cruise missiles when we need to track objects on high speed. And as for training, the issue for this task is that there is no open source validation and training dataset, and that overall the process is pretty error prone and time consuming, since you need to correctly not only just place bounding boxes, but also continuously place correct IDs. Also, as has been shown from previous works of ours, that models that are trained on a huge amount of general data do not work well on military use case. So yeah. Before we dive into the related methods and different kinds of approaches, I'd like to introduce our main metrics. So the first metric is HOTA metric. Basically, this metric tries to strike balance between detection and re-identification, so that we so that we do not go too far in one direction. So basically, we try different thresholds, select true positives from our predictions, and then we have a weighted metric between detection quality and identification quality. Another important metric is identity of one, which heavily penalizes missing and incorrect re-identification across our videos. So let's firstly give some attention to traditional methods and why they do not work in low FPS conditions. So the most mainstream approach to tracking is tracking by detection, where you firstly use some detector that gives you bounding boxes, then you train a detector that tries to associate those detections between frames. The most common example is deep sort, which after detection tries to model the motion using some heuristic model like Kalman filter, which assumes some kind of linear motion, and also tries to match using deep convolutional embeddings. So it's kind of combination, but on the last stage, it uses intersection of reunion for matching. And as has been proven by studies, this heavily decreases the methods that rely on intersectional reunion face drastic drop in performance. So, for instance, here, like the main methods have suffered twice a drop. So overall, it happens because in low frame rate environment, displacements between frames are huge, and sometimes intersectional reunion is pretty small between them, and the angles also change, and we need to train better representations to match those entities. And also they rely on heuristic motion modeling, which does not learn from the temporal data. Well, an obvious kind of solution is using transformers for a case of low FPS, and because it has great memory and it learns from the motional patterns. Well, in terms of transformers, it all started from detection transformer, which uses visual transformer for processing images, and then using Hungarian matching, it tries to match bounding box predictions. A great state-of-the-art example is memory multiple object tracker that has its own memory module that stores objects in 3 different states. So there is a state called new or active that is related to objects that are present in latest frames, and there is also a state, this kind of stale state, that objects have been out of frame for quite some time, and there is also like another state that for completely for objects that have not been present for more than certain threshold, so they're kind of forgotten. And overall, these methods have great performance, but they all rely on supervised data, so they're completely supervised. And the issue, as I said, is that tracking annotations are pretty costly, and many projects, many Ukrainian projects in UAVs have huge data sets for detection, but not for tracking. And so that's an issue. So that's why we've went into the domain of self-supervised methods. So in our previous work, we have tried out the model from some of the previous year called matching anything by segmenting anything. Basically, it takes any backbone, extracts the features, and then kind of using an adapter, it converts those embeddings to a layer of the model, the model's embeddings, and then it tries to match pixel by pixel, so that we do not avoid any necessary, any important scene details, which also helps in huge scenes in military context. And here are results from our previous work. So basically, we can see that we have compared our model against DeepSort, other traditional methods, and those, while those struggled, our model has achieved quite good performance. But one issue that was clearly identified is that matching anything by segmenting anything model struggles with short-term memory. So it stores the object just for, it does not have a complicated hierarchical structure for stored entities, and it also stores objects generally for like a couple of seconds after they go out of frame. Another new model that has came out just recently, a couple of months ago, that has solved long-term memory problem is Samba motor, which is now a state of the art for long-term memory tracking. Basically, they use graph-like structure for maintaining. So where edges are the similarity or between different tracks by their trajectory and appearance. And if we notice that those nodes are too similar, then we merge them and we avoid RAID. So we avoid assigning a new ID to the same object. So as for our research objectives, we've decided to improve our models as we have trained with state-of-the-art long-term memory modules from transformer, from memory multiple object transformer, and to take also SSM memory model, so with those graph structure from this latest Samba tracker. And we also aim to collect our training set. So in a previous work, we've collected a benchmark for this task, and we now also have collected a training set and annotated it, and we intend to evaluate it on our dataset, all those methods. So for our datasets we have collected, we have 3 classes. The first class is lightly or not armed vehicles. So that's basically some lightly, this military armored cars or just some kind of logistics vehicles, but with some weaponry. Another class is are trucks, either trucks that transport fuel or personnel, etc. And another third class is larger with multiple launch rocket systems, tanks, and so on. So here's statistics for dataset. So we have collected 119 videos from diverse sources, like from Telegram, YouTube. We have gone through a huge number of videos. The issue with collecting these videos is that in open source sources, there is a lot of shifts between tracks, so we do not have a continuous sequence. So you always have some kind of pop out of another video. So it was quite difficult to collect this amount of videos, but yeah. So total number of frames is 1800,000, number of bounded boxes 59,000, and also we have 14% of data from collected from winter. We also have some data collected from reconnaissance units on the Kharkiv front. So here is a distribution of our of length of our data set. So number of frames of an object. The object is present, and here's distribution by classes. So as expected, the larger class is much bigger. So this heavy armed. So here's an example for a dataset. So it is also been converted to low FPS. So that's an example. And so how do we intend to improve memory? So in more detail, so we want to, as the first stage, we would, as in the Massa model, we would extract features from using some pre-trained extractor. We would also get short-term memory predictions from Massa, but also we would get long-term memory predictions and closest embeddings using this multiple object transformer module, and then depending on which prediction has the higher confidence, we will take this prediction. And for Samba integration, we would basically do the same thing, but we would have this graph-like structure, and where we would have this nodes accumulate information over time, and where we also would take embeddings by higher confidence, and thus select an object. So as for our evaluation pipeline, we will use 3 different data sets. So the first one would be segment anything, a huge data set of 1 billion, so which is more general. The second, it would be our dataset, but annotated with pseudo labels. It's annotated with detection annotations. So detector was trained on nearly 1 million images on proprietary data, so it's disclosed. And the third one is our dataset, our annotated dataset, and we will evaluate on our benchmark. So yeah. As for future work, for now, integration is in process. The dataset has been completely annotated, and we have pseudo labels also. So yeah, as for future work, right now we're after integration, we'll evaluate using our pipeline from conference, and we will deliver some results. So yeah, that's it from my side.
Thank you very much. Do we have questions? No. Coming.
It's working. Okay. Yeah. What's your motivation? I'm kidding. So I have 2 questions. The second one maybe is completely irrelevant of the first one. So first question is, what is the reason for 5 FPS? Why so low? And can it be like extended to bigger FPS? And does it even like possible? Is it even possible? And the second question is like I'm not familiar at all with the technology. I assume that such model can fit on the UAVs, but can you just elaborate a little bit on the like requirements and stuff that goes onto actually like using the model on the drone itself? Thank you.
Yeah, so as for 5 FPS, this has been so we started developing this benchmark in scope of our paper submissions that we have done previously, and we have decided on this size due to the task of some stakeholders. So basically, we just the data that was coming was 25 FPS, and we would just take each 5 frame. So yeah, and for integration, as integration goes, these models would require. So for now, we intend for those models to run on the cloud, since they're huge, and we intend for them to be used in a kind of a centralized analytics more than just on a drone. But actually, right now, so if Word was to be deployed on drone, then it would require significant quantization. And actually, we are working right now on it, but it would require a more expensive hardware. So, like for instance, NVIDIA Judson, for instance, I forgot the name. Sorry. Xavier.
Okay. More questions?
First of all, thank you for your presentation. Second of all, I have 2 questions. The first question is, what is the self-supervised part here? Because it looks for me as a semi-supervised, because we have pseudo labels, you have labeled data set. And the second question comes from labeling. So you have light vehicles, unarmored vehicles, and in the example you have BTR. in the light vehicles. Can you please show this page? The data set. Yeah. So it's a BMP1 or BMP2, and in the class tank we have BMP3, BMP2 that would be almost the same from the UAV height.
Yeah. So this vehicle is called MLTB. So it's pretty similar, yeah, to BTR, but they're a bit different. So they're a bit different in their appearance. So basically, so it has quite a bit different corpus, a bit different form. So and our model can so it has been shown to distinguish those classes. So maybe this picture is not that representative, but overall we have noticed that the model mostly looks at the wheels to distinguish between those two vehicles because they have different wheels. And yeah, and as for the supervised part, it's actually self-supervised since as for pseudo labels, we get detection labels, not tracking labels. Tracking labels we use just for evaluation. And we also, for our tracking dataset, we have a tracking dataset for military for military AV footage, but we are using it just as a detection dataset. So,
thank you. More questions? Okay.
Yes. Thank you, Magita, for the presentation. So I have a follow-up question on this low FPS. So as far as I understand, the bottleneck is computational time. And if, for example, in the future, we would have platforms that would be capable of processing, say, at the original frame rate, then this low FPS adaptation wouldn't be needed, right?
well, overall, it helps. So in terms of how it works, it kind of improves how when between frames you have a big difference of between objects, then it's so our approach improves how it matches those objects. So for instance, if you have some footage where there is rapid change, like, I don't know, sports analytics, maybe when person changes angles constantly, then it might also be helpful. So not only in low FPS scenario. Yeah, so in terms of low FPS applications, I think, theoretically, in the future, we won't need to reduce the amount of frames. But for instance, when we have high speed, as I said, with cruise missile, then we have, like, for instance, speed of 2 kilometers in 2 seconds or something like that. So so displacement is quite huge, and yeah, it's not in such cases it's not a really near future that we could allow this. So yeah.
Okay, and so you were saying low FPS, and it's just sampling frames, or do you have, I don't know, some maybe adaptation pipelines that would do a smoothing or something like that?
Yeah, just sampling frames. Yeah, just.
Okay. So my next question is on multiple instances. For example, if you have, so do you output the unique instance ID per each vehicle instance? For example, you have 2 cars and then they look completely the same, and you output ID1 and ID2, right? Or you output, for example, ID, like car and type. So what's
So if there are two same vehicles but on the same frame?
Yes.
Well, I think it would. It's a good question. So usually on our data, we always have difference between the instances. But yeah, actually, due to how it matches the objects, it might give the same ID for those.
For example, if you have two tanks on one frame, then what will be your model's output? ID tank for both tanks, or ID1 and ID2?
ID1 and ID2 and class tank. So it both classifies and gives IDs.
Okay, and have you maybe observed such cases when both of them go out of frame and then only one is captured, and is your model still accurate in that cases?
Yeah, so for like, so as I said, the issue was that if it was covered by smoke or maybe it went out of frame, the model that we've trained had bad memory, so it remembered for like 3 seconds maybe, and then it reassigned a new ID. And so that's how we intend to fix it, to basically to have a more sophisticated memory to assign the same ID as it was. So yeah.
Okay, and my final question. During your presentation, you was quite often mentioning we. So we did this, we did that. And what was your contribution particular?
Yeah, so we both were thinking about different models and gathering the data set. And do you mean the part of diploma or the part?
Yes.
Yeah, for the diploma part, I guess everything was mine. So yeah, maybe I should have used different wording. So yeah, we were with Igor, was my advisor. We were continuously discussing different approaches, but in terms of implementation, that was on my part.
I mean, I know a little bit more context that you also have a publication, and so my question is, so whether the work you are presenting is unique, is yours, or you are porting something from that paper and presenting as?
Yeah, so on the terms, so in terms of paper, so it has so kind of the paper ends here. So here's the metrics from the paper, and then improvements, propositions, and new data set is from my part. So, yeah.
Okay, I see. Thank you.
Yeah, so if possible, if we still have 1 minute, I would like to ask the question. First of all, I would like to thank you for this presentation. So you mentioned that how you collected the data, and I would like to ask if you used any like data augmentations, and if yes, then which one?
So for data augmentation, I have used one of the approaches was like what Ruslan has suggested. On the seminars, we have sampled different combinations of this 5 frames from 25 frame rate, and also yeah, we have changed light slightly, and yeah, and also we changed the angles. So yeah, basically, yeah, that's it.
Great, thank you.
Thank you very much. More questions from the virtual bot? No, thank you very much. That was the last presentation in the session, and I would like to wish you to enjoy your lunch break. You know the schedule. We'll continue exactly on the schedule.